Okay, so you've just been given $50 million, and your task is to create a chip company. What goes into designing a chip and manufacturing it?
I'm glad they gave me $50 million to start a chip company because I've been working on it for a while now. Okay, let's get started. Find some customers, ask them what they want. What are the inputs? What are the outputs? Am I making a chip for an elevator, or am I making a chip for the latest GPUs or phones, or what am I doing? Ask them for what they want. And once I get that, there's a team, right? There's a high level team. This is just a bunch of directors or like all the high level people who are just um, trying to discuss and see what's important. Like how much should we have 4 gigs of RAM or 6 gigs of RAM? Should we have a 4K camera or a 1080p camera? Is
Okay,
that
so
fine?
let's say like we have all these like specifications laid
Yeah,
out for you,
yeah.
and you know what the consumers want, right? What goes into designing it? Like, what does that mean to design a chip?
Okay, perfect. So once that is done, next there's a bunch of coders who work on hardware designers who work on C, C++, that kind of high level languages to come up with the exact same design and simulate it, see that whatever, specifications are given required work, right? Because you don't want to get into the nitty gritty, do everything, and then next thing you find out, oh, we designed the entire chip with 2 gigs in mind, and well, it can't work with that, and then you need to repeat the entire process again. So there's a bunch of high level designers that work on that, see that the project will work, make some predictions, make some numbers so they can present, that kind of stuff. And once that's done, then it gets to the designers. The designers do the hardware design. And there's a bunch of different languages for hardware design, like Verilog, VHDL, System Verilog, a bunch more. I think these are the common ones. And then they start designing, right? And when I say designing, it's just coding pretty much, right? Let's just say coding can do anything. And they do all this coding. And once that's done, you have your design. This is going to be your processor. But as of now, it's just a lot of lines of code. So how does this become a physical chip?
Mhm.
The next thing, once these guys are done with the design, is design verification, which means, hey, somebody wrote a lot of lines of code, but does it work? Did they make a mistake? What if they made a mistake? What
Does
if
it
there's a
meet the specification?
uh,
Right? Does it meet the specification?
yeah, exactly. And like let's say somebody's making a calculator, right? And the designer wrote code for addition, subtraction, multiplication, division, right? But then the designer didn't necessarily write any specific case for divide by zero or something like that. Now, if somebody were to buy that calculator and everything happened and you had a chip and somebody bought the calculator and did divide by zero, suddenly I don't know, let's say the calculator overheats or, it never works again. Like you don't go back to the main screen, right? Something like that. So you have design verification exactly for these things to find the corner cases, to see if the design is meeting the specs, to see if it's working normally, just generate a bunch of test cases and see if my design is functioning the way it's supposed to be functioning. And that's exactly what they do. And there's a lot of back and forth between all these teams, obviously. And
But we're still at the like lines of code, right? How does this
yeah,
get into like a physical product?
yeah. There's a way to go. So, anyways, once the design verification is also done, then also these are all not things that happen in serially. They also happen parallelly so that you can save time in the industry. But yeah, once the design is fine. Next there's a step called synthesis. This is a fancy step because I don't think software has any of this stuff, right? Because in software you write code, you verify it, and then it's for the most part it's done. You have your code or app or website or something like that. But now you have synthesis, and what synthesis does is, somebody takes all these lines of code and converts it into wires, basically wires and gates. And when I say gates, it's just AND gate, OR gate, NOT gate. For yeah, but anyways,
Simple logical gates.
simple logical gates. AND gate is just, hey, I have everything in hardware is just ones and zeros.
Boolean.
That's it. Yeah, it's just ones and zeros. So an AND gate, what it does is if both my inputs are one, my output's going to be one. Otherwise, it's going to be zero. OR gate is if one of my inputs is one, output's going to be one. A NOT gate just flips whatever the input is, right?
So with these like simple logical gates, you can represent any arbitrary like addition. You can do multiplication. You can do everything basically.
Your phone, for the most part, honestly, is just ones and zeros. Everything is just ones and zeros. That's honestly why I chose this industry, right? Because it's super simple. It's easy to understand. It's just ones and zeros, and it's also like super intriguing. It's like, oh, how can you do so much? Like how is my computer doing so many things, but you're saying it's just ones and zeros? Wow.
So like we're at the synthesis part. What
Yeah.
happens next?
Okay. So now your lines of code have been converted into gates and wires. Now what happens after the synthesis step is there's something called physical design. And physical design, they take the synthesis steps. Like you're still seeing after synthesis, you're still seeing a picture on a computer. It's not lines of code, but it's a diagram now, but it's still on the computer, right? Now physical design takes this. They use softwares to draw these gates so that it can go onto a physical board. Like this is how it's going to be placed. Because in the diagram, like, everything is just placed here and there. That's it. But when physical design takes over this, like they're placing the gates as compact as possible. They're placing it so that, everything is as perfect as possible, like achievable. And as far as the chip is concerned, this is very important for any chip you're making. Three different things. Area, the smaller the chip, the better it is. Because you're putting all these chips in phones, right? And phones, you're looking for smaller dimensions. You want like a smaller product. The smaller the phone is, the easier it is to carry. So you want the chip to be as small as possible. And also, if the chip is small, that gives you more area for like putting your cameras or other fancier things like speakers or other things for your phone. So yeah, the smaller the chip, the better. Area is very, very important in any hardware manufacturing. Next thing is power. You don't want to make a chip and then next thing it runs out in like 5 minutes, right? Because if you don't design something properly, it can run out of power in no time. Um, your chip can melt if everything is on. So the second one is power, and the third one is timing. Obviously, you want the chip to be as fast as possible. You don't want something that's super slow. So yeah, these are the three main qualities. And then yeah, physical design, they take it, they place everything so that you get the minimum area possible. And yeah, also other teams like power teams or other teams, something like that. They're also working to kind of optimize for power. Um, and again, then there's timing, right? Each gate, when a signal passes through the gate, it takes a specific amount of time. And you want to see to it that, you don't place the gate such that it takes too much time or too less time. Because for the most part, there's something called a clock signal, and then there's a lot of stuff. But basically, there's clocks that kind of simulate a bunch of stuff. Maybe I'm getting too much into the nitty-gritty details, but yeah.
So
Um,
now you have like something that actually can be manufactured, is what you're saying.
Exactly. Now you have something that's ready. It's the final thing. You have it's again pretty much a diagram, but you have the final thing that can now be manufactured. So once this is ready, you give it to you would ideally, there's one more step, I'll get to that in a bit, but you ideally give it to the foundry. And the foundries are like companies like TSMC or Samsung. These are the guys that manufacture the chips, right? And they give it to you. And so you give it to them, and then what they do is they have to, industry. Do you have a question?
So they basically make like a mask, right, or something. Where
Yeah,
they
exactly.
shine like a like laser or something into it, and they etch silicon so that they can actually get the
Exactly. Pretty.
physical
Yeah.
dimensions and whatever.
So yeah, the physical everything is everything is just semiconductors, right? So and they take like wafers, there's different wafers, and then they have different processes. They like have masks, as you said, shine ultraviolet rays, like that's what creates the wires, because these wires are not like the wires you see at home, right? Not at home you can just like hold this wire, we have so many wires right here. But the wires we're talking about, when we're the latest nodes are like 5 nanometer, which means your wire is like, imagine it's like 1 billionth of a millimeter, right?
That's
That's
like
how small they
yeah,
are.
smaller than like a strand of hair,
Yeah,
right?
it's so much smaller, right? So its accuracy is very important, and everything has to be perfect. And that's, yeah. So they do a bunch of stuff, and then they print. They have like big wafers, like circular wafers, and they print like hundreds of the same processor on that, and then they cut out each processor individually.
It's
Because
like something else that like having smaller area would help with, right? You can fit more chips on each wafer, so it'd be less costly.
exactly. So the industry works in such a way such that each machine prints on one wafer. So if your design is smaller, that means you get more processors or more of your design per wafer, which means you're saving a lot more money there, right? If you could only print like one processor per wafer, that means you're just spending like your let's say your iPhones would cost maybe like, I don't know, like 50,000, $100,000, right? Anyways, so yeah, they print this and then they give it to you, right? And then it should work. But the thing is, I just told you that these wires are so thin, so small, you cannot see them.
Yeah.
So what happens if two of these wires are shorted, what happens? It's a processor. It's a very complicated processor with millions and billions of transistors.
So you're saying like it's not always accurate? Like there's like wires that just doesn't work in the
Yeah,
wafer?
imagine I asked you to place two different rulers parallel to each other. How do you know that they're perfectly accurate? Like, maybe wind could move it a little bit or something, right? Or like
At
that
a
could be any.
nanometer scale, you don't know, I guess.
Exactly. It could never be that parallel. So if like two of my wires are shorted, that means like, hey, you just spent like you gave me $50 million, and I just spent like, I don't know, $30 million, and it was all for nothing. So I got to start over again. So yeah, that's why before we give it to these foundries to print on wafers and make these processors, there's one more team. It's called the DFT team, Design for Test. And what they do is they pretty much like whatever the area of the chip was, they pretty much add like 40% area, which is a lot of area. And I just told you that area is very important. But it's very important that they do this. And what they do is they add a lot of extra circuitry and extra stuff so that once you have your wafer back, let's say two wires are shorted, you can pinpoint which wires are shorted, right? Because if you can't do that, then it's all for nothing. But if you can pinpoint which wires are shorted, and if you have multiple processors that have the same wire shorted, you could just go back to physical design and say, hey, can you place these two wires a little bit away so that they don't get shorted because there's some issue with the manufacturing somewhere, right? And suddenly, voila, I didn't waste my $30 million. I just maybe another million and my chip is fine, right? So that's what the DFT team does, and it's very important. And once all of this is done, your chip is back. You test it, everything is good. There's a few back and forths. You want to do a few iterations so that you get the best product possible. And once this is available, then you give it to, like there's like different emulation. There's okay, I guess emulation's a different thing. I'll get to that in a bit, but there's like OS teams who like write operating systems for this. Then software takes over, and then it just keeps going. And yeah, they put it in a product, give it to you, voila, you have a beautiful iPhone. And yeah, that's pretty much how the hardware stuff.
What was the emulation stuff you're talking about?
I'm glad you asked. Yeah. Emulation is so yeah, while all of this is happening, again, I said all of this doesn't happen serially. A lot of things do happen parallelly, but then this is pretty much the serial order in which things can happen. So the teams I mentioned earlier work a lot earlier than the teams I mentioned later because each team's output is the next team's input. And like as I said, there's a few iterations, so all teams end up working parallelly, but there's an emulation team. Till the chip does go till you get the actual wafer, till you get the actual processor. There's a bunch of emulation teams, and what they do is there's something called FPGAs, which are fully programmable gated arrays. Is that
Field
right?
programmable gate arrays.
Yes, thank you. And they kind of just emulate whatever your final product is going to be, and they try to emulate it.
So, like the input for that would be the logic gates that you talked about.
Exactly. So let's say for simpler terms, let's say my design has 100 AND gates and 50 OR gates. An FPGA might have like 1,000 of AND and OR gates, right? I'm just gonna simulate 20 AND gates and 15 OR gates, how much ever I said, and try to see if I can emulate the exact processor that I'm making, and just test it out, right? So I can have my future teams, like all these DFT teams, be more
Software
ready for
team
this.
and OS teams can start using that chip before the actual thing's back.
Exactly. And then once that comes back, they can just like, just it's kind of like more like plug and play. Not exactly, but close enough. And I think yeah, I think that's pretty much it. Yeah, yeah,
Nice. I think that's a very good overview of
yeah.
like from start to end.
Yeah,
So if someone wants to start a chip company, this is basically the high level overview of how they
exactly.
get to
Yeah.
it. Nice. Okay. Well, we're gonna end it here. But if you have any questions, please be sure to leave a comment below or email us at twobrownAccents@gmail.com. And
You
one
guys.
new announcement that we're gonna make today. You wanna say it?
Oh yeah. From now on, our podcast is not going to be bi-weekly. It's going to be weekly. So woohoo.
Every week you get to look forward to us talking about something new.
Exactly. And you're listening to Two Brown Accents. I'm Surya Ramesh.
And I'm John Ravi. And we'll
Peace.
see you in the next one.
Yep.